everyone, thanks. I'm David Woodruff. I'm from Carnegie Mellon University. This is joint work with Deanna Needell and William Swartworth. The title of the talk is Testing Positive Semidefiniteness and Eigenvalue Approximation. So let me start by giving an introduction to what we're going to talk about. So we're given a symmetric matrix A. It's real symmetric, so it's D by D. And we ask the question, how many linear measurements of A do we need to distinguish between case 1, A is positive semidefinite, and case 2, A has a large negative eigenvalue. Okay, and let me define what linear measurements mean in a moment. PSD for us is going to mean symmetric PSD. Okay, so it has real eigenvalues, and PSD means all the eigenvalues are non-negative. And let me give you an example why we might care about this problem. In terms of trying to access A implicitly through what I'm going to call linear measurements. Okay, so A could, for example, be the Hessian of a loss function f of a neural network evaluated at some point x0. And so A is not given explicitly, and it'd be very expensive to form the entire Hessian matrix of a large neural network. And why might this be important in the context of distinguishing these two cases, 1 and 2? Well, in case 1, it would correspond to a loss function f being minimized at x0. That's when the Hessian would be positive semidefinite. And case 2 would correspond to f having a steep descent direction at x0. That's what it would mean to have, for the Hessian to have a large negative eigenvalue. Now, as I said, this matrix A is not given to you explicitly, so instead you're going to access it through what I'm calling linear measurements. And there are certain kinds of linear measurements that are quite natural. For example, matrix vector products. In this case, even though A is not given to you, what you can do is choose a vector V and observe the matrix vector product A times V. You can then adaptively choose your next vector, W say, and then observe A times W. And W can be a function of your previous output, A times V. Now, why is this a natural model? Well, for example, in the context of neural networks, if A is the Hessian, then you can actually compute Hessian vector products using automatic differentiation, or if you're familiar with it, Perlmutter's trick. And so this is an efficient way to access A without actually having A explicitly. Another example is bilinear form queries. So here, what you do is you compute U transpose AV. This is just a number instead of a vector. And you get to choose U and V. You observe this number, and then you get to choose your next pair U and V, and so on. So this is a way of adaptively accessing A. And interestingly here, again, A does not need to be specified explicitly. U transpose AV can be approximated with only 4 queries to F using finite difference approximation. And this corresponds to a single second derivative calculation. Okay, so you can access A, this large matrix, implicitly with matrix vector products and bilinear form queries. And both of these are specific kinds of linear measurements. Linear measurements are also natural for streaming and communication settings. I won't get into the details, but under some assumptions, the best possible streaming algorithms for any problem actually consist of linear measurements. And this is natural because, for example, if your matrix A is distributed across multiple players, or if it's updated in a stream, then since this operation is linear, then given A times V and A prime times V, you can add them together to get A plus A prime times V. So this is a very important mergeability property of linear measurements. Okay, so that's what we're going to look at. We're given this matrix A, and we'd like to observe certain properties of it through linear measurements. And to formally define this problem that I talked about PSD testing, though we will look at other problems later in the talk, we have the following definition. So we say an epsilon LP tester outputs true with constant probability, let's say 3/4, when A is PSD, and it outputs false with constant probability, say 3/4, when it's sufficiently far from PSD, meaning that its minimum eigenvalue is, say, less than minus epsilon times the p norm of A. So here it's important that we have a scale invariant quantity. I didn't just put minus epsilon on the right-hand side. I put minus epsilon times a norm of A, because then if I scale A by any constant, both the left and the right-hand sides get scaled by the same amount, so this condition still holds. Okay, so it's a scale invariant problem. And now what do I mean by this norm of P on the right-hand side? Well, this is called the Shadden P norm, and all it is it's the vector P norm of the eigenvalues of A. Okay, so it's the sum from I equals 1 to d of the absolute value of the ith eigenvalue lambda I to the p, all raised to the 1 over p. Okay, so a particular importance we'll look at is when p equals 1, this is just the sum of absolute values of eigenvalues. And when p equals 2, this is just the Frobenius norm of the matrix A, the Euclidean norm, entry-wise Euclidean norm of the matrix A. We want to ask ourselves, how many queries does an epsilon LP tester need to distinguish between these two cases? So in the first case, it's PhD. In the second case, it's sufficiently far. And we look at the different models we discussed. For example, the matrix vector query model, the vector matrix vector query model. General linear measurements are also can also be looked at, though we don't look at them here. And this is where you take your matrix A and you just vectorize it. So you think of it as a d² dimensional vector, and what you have is m is a vector, and you just take the dot product of these two vectors. Okay, so these are the different query models that we're going to look at. And we're going to consider both adaptive and non-adaptive testers and try to get tight query complexity bounds in these different models. Okay, so adaptive means I get to choose my next query as a function of my previous query. Non-adaptive means I specify all my queries up front at the beginning. Okay, are there any questions about the problem? Okay, good. Feel free to stop me at any questions, or if there are any questions in the chat box, I'm happy to try to monitor that as well. Okay. Okay, so let me move on now to matrix vector products then. And yeah, so matrix vector products are arguably maybe the most natural model you could look at here. There is sort of a common model in hardware where you just a lot of scientific computing explicitly looks at the number of matrix vector products as a natural measure for complexity. This is important because things like GPUs can process multiple vectors at once, and so this is really perhaps arguably more important measure than time complexity. So as I said, the problem is scale invariant. So what we're going to do is we're just going to assume that the Shannon 1 norm of A is 1. We're going to look particularly at p equals 1 first. And what we're going to try to do is use Krylov iterations. Okay, so Krylov iteration is a very useful technique for finding the maximum eigenvalue of a matrix. And if you're familiar with power method, then that's exactly what it does. It iterates through vectors and tries to find the max eigenvalue. Okay, now what we need here is that our matrix A is positive semidefinite to run the Krylov method. So what we're going to do is we're going to negate A and shift it. So let me describe what that means here. So here's a picture of the eigenvalues of A. We have a negative one, potentially this red dot, and a bunch of positive ones, these blue dots. And this negative one is at most negative epsilon times 1. We assume the 1 norm is 1. And so we first negate A, and what this does is it flips the blue eigenvalues to be negative, and it flips this potentially existing red eigenvalue to now be positive. And then we shift by lambda I, so we're adding a multiple of the identity, and we choose lambda to be larger than the max eigenvalue of A. And so by doing this, whether or not this red dot exists, it makes all the eigenvalues positive. Okay, so negative A plus lambda I is now a PSD matrix. Okay, now we'd like to detect the existence or non-existence of this red dot. And so what we want to do is we want to estimate the max eigenvalue of this new matrix, negative A plus lambda I, to within epsilon additive error, right? Because you see that there's this gap of epsilon between this red point and the closest blue point. And after shifting, negating and shifting, this gap of epsilon still exists. Now, this lambda that we shift by, we shifted by lambda to make the matrix positive semidefinite. This lambda could be as large as 1, right? It's not larger than 1 because the sum of absolute values of all the eigenvalues is 1. And so we need to estimate the top eigenvalue to within a multiplicative 1 plus or minus epsilon, right? Because the top eigenvalue might be 1, this red dot after shifting, and the closest blue dot might be 1 minus epsilon. So to detect its existence, we need a method to estimate the top eigenvalue of a matrix to within multiplicative 1 plus or minus epsilon. And if you haven't seen it before, one of the coolest tricks in this area is the Chebyshev trick. This allows us to estimate the top eigenvalue with 1 over square root epsilon matrix vector queries. Okay, I'll show that on the next slide. You might be more familiar with the power method, which just iteratively multiplies and tries to raise the largest eigenvalue to a certain power. That would take 1 over epsilon matrix vector products. And this is going to do better, 1 over root epsilon, which is significant if your accuracy epsilon is small. So here is the Chebyshev trick. We have a PhD matrix M in our application. What we did is we negated the eigenvalues of, we negated A and then we shifted A. It was PhD. And what we do is we choose a random vector V, for example, a Gaussian vector. We compute V, M times V, M squared times V, and so on, M to the K plus 1 times V. So this is very adaptive. We take our output from the previous query and we feed it into the next query. And what we know when we get the answer to all these queries is we know how M acts on the entire Krylov space. Okay, so the Krylov space, what this is just all polynomials of degree at most K applied to the eigenvalues of your matrix M. Okay, so you take your matrix M, you keep the same eigenvectors, but each eigenvalue, you replace it with a polynomial of that eigenvalue of degree at most K, the same polynomial on all the eigenvalues. Okay, and this gives you this P of M, and we know what P of M times V is now for any polynomial P of degree at most K, because what we can do is we can just multiply the outputs that we got by the coefficients of the polynomial and add them together. Okay, so we get any polynomial of the eigenvalues. And a really cool fact from approximation theory says there exists a polynomial P of X of degree K, which is order square root lambda 1 times 1 over square root epsilon times log 1 over delta, such that this polynomial evaluates to 1 on lambda 1 and evaluates to at most delta on any argument x, which is sufficiently far away from lambda 1. Okay, so think of having an interval. For us, lambda 1 is at most 1. So we have an interval, a subinterval of 0, 1. Let's look at 0, lambda 1 is our interval. And on lambda 1, the polynomial is 1. And if I move additively epsilon away from it, the polynomial evaluates to at most delta. Okay, so this is exactly the interval that we have because our matrix is PSD, so the minimum eigenvalue is 0. That's why x is at least 0, and it's at most lambda 1. Okay, so yeah, so what happens now is great because this polynomial evaluated at M times V is going to align very well with the top eigenvector of M. And so this Krylov space witnesses the largest eigenvalue of M to within epsilon additive error. Okay, now one question that comes up a lot is, well, you don't know what this polynomial is. It's somewhere inside of this Krylov space. How are you going to figure out what it is? Well, you don't actually need to know what it is. Okay, you know it exists, and what you can do is you can just optimize the quadratic form over this Krylov space. And you'll find on this slide, you'd find the top eigenvalue. If it's epsilon away, and in general, by doing this negating and shifting reduction that we did for PSD testing on the previous slide, we'd be able to locate a negative eigenvalue if it's sufficiently far away, negative epsilon times the Shannon 1 norm of A. So this is how we solve our problem, and the Chebyshev trick gives us 1 over root epsilon matrix vector products. And so a question I like to ask is, I don't know if this is can be an interactive audience, but a question I like to ask is, do you guys think that the 1 over root epsilon matrix vector products is optimal for this problem? Okay, I'll just let you think about it for a second. Okay, it turns out that it's not optimal. And pictorially, what's happening is we're shifting by too much. Okay, so if you remember the picture of A's eigenvalues, this was the picture. The blue dots were the positive eigenvalues. The red dot was the negative eigenvalue. Then what we did here is we negated and then we shifted. And we had a shift by potentially this value lambda times identity, where lambda could have been as large as 1. And that shifting caused us to need a 1 plus or minus epsilon multiplicative approximation to the top eigenvalue of the shifted matrix. And that was kind of expensive. We ran Chebyshev trick, and we needed 1 over root epsilon iterations. So instead, the idea is, well, what if we could somehow use a small number of matrix vector products to first remove the largest eigenvalues of A? You see these gray dots here. If we could somehow eliminate these first, then what would happen is, now when we negate, here's the negative of A, we flip the spectrum around 0, this little black tick mark, and these gray dots, they don't exist because we removed them. And so now when we shift to make all the eigenvalues positive, well, we don't have to shift the red dot over as much because these gray dots, they just don't exist. Okay, so the idea is, can we somehow use a small number of matrix vector products to remove the top eigenvalues and then do the procedure that we just talked about, so we don't have to shift by as much? And so then we can afford a weaker multiplicative approximation, which means we can invoke the Chebyshev trick with a smaller number of matrix vector products. That's the idea. So let me just say it quantitatively. So the idea is, well, let's try to deflate the top T eigenvalues, where T is roughly 1 over epsilon to the 1/3. Okay, so deflate, what that means is to remove those eigenvalues. It's approximate, but I'll describe more about how we actually do it in a moment. If we were able to do that, then, well, we know that the original sum of absolute values of eigenvalues of A is 1. Okay, now after deflation, well, what could the maximum eigenvalue be? Well, we've removed the top 1 over epsilon to the 1/3 eigenvalues. Okay, now that means the remaining eigenvalues, their value can be at most epsilon to the 1/3, right? We can have at most T eigenvalues that have value at least 1 over T. If we remove the top T, then all eigenvalues are at most 1 over T, and 1 over T would be epsilon to the 1/3 for us. And now when we do our negating, we're negating A minus T. That means A with the top T eigenvalues removed. And then we're shifting by lambda I. Well, now we can set lambda to be order epsilon to the 1/3. And the significance of this is now when we do our shifting, well, the max eigenvalue is going to be order epsilon to the 1/3. Okay, and we know that there's a gap between when we do our negating and shifting, the max eigenvalue, the gap is still going to be epsilon, like what it was before. But since the max eigenvalue is epsilon to the 1/3, epsilon is only an epsilon to the 2/3 fraction of that. So we only need to multiplicatively approximate the largest eigenvalue with 1 plus or minus epsilon to the 2/3 approximation. And importantly, now when you feed that into the Chebyshev trick, you can replace epsilon with epsilon to the 2/3. You get the square root of that, and now you only need 1 over epsilon to the 1/3 queries. Okay, so that's the main idea. You might be asking, well, how did I get rid of the top eigenvalues? What is this deflation thing? It turns out there's an explicit algorithm that uses 1 over epsilon to the 1/3 matrix vector products to remove the top 1 over epsilon to the 1/3 eigenvectors. That's a work of Musco and Musco. But in fact, we don't even need to do this explicitly. This Krylov space is so flexible, we can do this implicitly. And let me say how that works. Well, instead of considering this fancy polynomial Q of X that I talked about, that kind of like is 1 on the top eigenvalue and then is roughly 0 if I move epsilon away. Instead, what I'm going to do is I'm going to take that polynomial Q and I'm going to multiply by x minus lambda 1, x minus lambda 2, and so on, x minus lambda t, where lambda 1 through lambda t are the top t eigenvalues. And so here's the picture of what's happening. Well, these top eigenvalues, these gray ones, we're actually explicitly setting them to 0 with this polynomial. So this polynomial p of x that we found, it's 0 on these gray eigenvalues, it's roughly 0 on these blue ones, these positive ones, and that's what we got by negating and shifting, and it's very large, close to 1 on this single negative eigenvalue. And you might ask, well, you know, I had to zero out all these eigenvalues, maybe my degree is going to go up. But it doesn't, because the degree of Q, remember, was 1 over epsilon to the 1/3. And the number of eigenvalues T that we removed was also 1 over epsilon to the 1/3. And so the product of these two polynomials has degree 2 over epsilon to the 1/3, which is still order 1 over epsilon to the 1/3. So the degree only changes by a constant factor, but now we can remove all of these large eigenvalues and execute our previous proof. So this, as I said, this polynomial Q is just the appropriately shifted Chebyshev polynomial that we had before. And now what we have is that, again, there's some polynomial in this Krylov space that we get, such that P of A times V is going to be very well aligned with the negative eigenvector. And just like what I said before, you don't have to know what this explicit polynomial is. It exists. And so what's going to happen is you just take your matrix vector products and you optimize over them to try to find a negative eigenvalue as a proof that your matrix is not PSD. If you don't find a negative vector, so that X transpose AX is negative. If you don't find one, then you just output that your original input is PSD. Okay, so that's the whole algorithm. In particular, if your input matrix happens to be PSD, you will always say that it's PSD. And with good probability, the probability here is only over this choice of random vector V in the for the matrix vector products. With good probability, this is going to be you'll find a vector in your Krylov space X for which X transpose AX is negative if A is actually far from being PSD. Okay, so that's the idea behind this algorithm. And just to conclude, what it says is there's an LP tester which makes order epsilon to the 1 over epsilon to the P over 2P plus 1 matrix vector queries. We studied P equals 1, we got 1 over epsilon to the 1/3, but this generalizes to any P. For P equals 2, you get 1 over epsilon to the 2/5. And you might be looking at these bounds and saying, there's no way this is the right thing to do. Is this the best possible? It turns out that these weird-looking upper bounds algorithms are actually optimal, okay, by a recent lower bound technique of Braverman et al. And this is kind of a cool hard instance that might apply to other algorithms that you might be looking at. It turns out that the hard instance is to look at a Wishart matrix. So a Wishart matrix, what it looks like is a Gaussian matrix G times a Gaussian matrix G transpose. And this matrix is positive semi-definite. It's a matrix times its transpose, so it has this square root, it's positive semi-definite. And what this paper shows is that you need roughly D queries if you have a D by D Wishart matrix. So G is D by D, so GG transpose is D by D. You need roughly D adaptive matrix vector queries to decide if the minimum eigenvalue is some constant C divided by D squared or the constant C divided by 2D squared. Okay, so the top eigenvalue of GG transpose is very well concentrated using random matrix theory, but the bottom eigenvalue, this Dth eigenvalue, is very anti-concentrated. It moves around, and with good probability it's C over D squared, and with good probability it's C over 2D squared. And you got to figure out which case you're in. And the way we can apply this to our problem is, well, we can take this hard instance, this Wishart GG transpose, and we can artificially subtract C over D squared times the identity. Okay, now if we're in this case where the minimum eigenvalue is C over D squared, then this new matrix is positive semi-definite. Otherwise, we subtracted too much if the minimum eigenvalue of GG transpose is smaller, and it would mean that this matrix actually has a large negative minimum eigenvalue. And you can quantify the largeness by setting D appropriately as a function of epsilon and P, and using this omega D lower bound, this ends up giving this matching lower bound for the LP testing problem. Okay, so I won't say more about that, but that's how you can show that this matrix vector product algorithm is optimal. Okay, so just to conclude, there was a nice balancing technique here where we first remove large eigenvalues, and then we applied this Chebyshev trick on the negated and shifted matrix And this is how we were able to isolate a large negative eigenvalue if it exists. Okay, that's optimal for matrix vector queries. Now, so that was sort of a warm up to this area. Let me look at another kind of query, which I mentioned early on in the talk, which is these bilinear sketches. Okay, so sometimes your matrix A is so large that you can't afford to just compute matrix vector products. The output, this big vector, might be too large. So you want to apply dimensionality reduction on both the left and the right of A. And one way to do that is to compute this quantity here, 𝐺𝐴𝐺 transpose. This quantity here, which I'm underlining. And so what you're doing is you're sketching on both the left and the right by, in this case, a Gaussian matrix. Okay, so G has standard Gaussian entries, so normal with mean 0 and variance 1. And the small dimension of G, that is the number of rows here and the number of columns here, is only 1 over epsilon. Okay, yeah, so you can compute this 𝐺𝐴𝐺 transpose, this very small sketch, with only 1 over epsilon squared vector matrix vector measurements, because you just multiply on the left and the right. You get a 1 over epsilon by 1 over epsilon matrix. It's very small. And the algorithm is super simple. So you accept, you output that A is PSD if 𝐺𝐴𝐺 transpose is PSD. Now, if A is PSD, then 𝐺𝐴𝐺 transpose is always PSD. And you reject otherwise. Okay, so if you can find a vector such that X 𝐺𝐴𝐺 transpose X transpose is negative, then this is not PSD, and you declare that A is also not PSD. So this is a one-sided tester, meaning that if A is PSD, you will always say that it's PSD. If it's not PSD, with good probability, you can show that you in fact will determine it's not PSD. And the analysis follows from known eigenvalue sketching results of Andoni and Nguyen. We're not claiming an improvement on that. But one thing you can do is show that this is optimal. Okay, so this for P equals 1, this epsilon L1 tester, if you sketch on the left and the right with these bilinear sketches, you need a 1 over epsilon by 1 over epsilon matrix. This is in work with Lee et al. The rough idea is to take a symmetric Gaussian matrix and add a spike to it. I won't get into the details. A spike means a large negative rank 1 component, or you don't add it, and you have to distinguish between the cases, similar to the lower bound technique we talked about earlier in the talk. But what about L2 testers? Okay, so L2 tester means, again, we want to accept if the input matrix is positive semi-definite, and we want to reject if there's an eigenvalue, a negative eigenvalue at most minus epsilon. So the negative eigenvalue is at most minus epsilon times the 2 norm of A, which is often called the Frobenius norm of A. Okay, so does there exist an eigenvalue that's negative and at most this quantity? And it turns out if you wanted a one-sided tester, meaning that you're always going to output its PSD when the input matrix is PSD, then you need a lot of queries. Okay, so there's a theorem we show that any one-sided tester, which outputs false with constant probability on all matrices on this particular spectrum, must make a lot of queries. Okay, so think of epsilon here as a constant. There's one negative eigenvalue that's negative root d. All the other eigenvalues are positive, they're 1. So this one negative eigenvalue, well, it's equal to actually negative times the Frobenius norm of A, which is about root d in this example. And what the theorem says is, hey, you need d queries. That's a ton of queries, right? It's a d by d matrix. We give different proofs of this lower bound. We give a direct proof and also a proof using ideas in communication complexity, if you're familiar with that area. But let me not get into lower bounds. We're probably here more excited about algorithms. So let me just say how we can get around this. So let's diagnose the problem. Okay, so what we're doing, a natural way of computing a small sketch of your matrix A, a small dimensionality reduction, is to compute 𝐺𝐴𝐺 transpose, like we did for P equals 1, But the problem is when you do this, the eigenvalues of 𝐺𝐴𝐺 transpose, they concentrate around the trace of A, and which is the sum of eigenvalues. The trace of A could be very large, like square root D times the Frobenius norm of A. So let me draw a picture. It's probably clearer than what I can say. Okay, so here's the picture. Okay, so A could have had negative eigenvalues, a negative eigenvalue, but when you compute 𝐺𝐴𝐺 transpose, it might have all positive eigenvalues, and these eigenvalues, they're going to actually concentrate around the trace of A. Now, if A initially had a negative eigenvalue, which was kind of far away, like at most negative epsilon times the Frobenius norm of A, then what's going to happen is that, well, although you have all positive eigenvalues, this eigenvalue is kind of a bit farther away from trace of A than the other eigenvalues. Okay, so what you want to do is you want to look at the positions of the eigenvalues relative to the trace of A. So the idea behind the algorithm is a very simple algorithm. You have a matrix, compute 𝐺𝐴𝐺 transpose, also estimate the trace of A. There are efficient sketches to estimate the trace of A. And you just reject if 𝐺𝐴𝐺 transpose has a suspiciously small looking eigenvalue, if there's some eigenvalue that's far enough away from the trace of A. Okay, so here is the formal argument. Again, earlier we were looking at scale and variance. We can assume the Frobenius norm of A is 1 by scaling. And our algorithm that I just said is, hey, let's just compute this quantity 𝐺𝐴𝐺 transpose. Okay, and what we're going to do is we're going to compute the minimum eigenvalue of this. And if it's suspiciously small, namely if it's less than the trace of A minus a quantity I'm going to put here, epsilon times k, we're going to say, hey, we're going to reject A. It's not PSD. And you can show that if A has a negative eigenvalue smaller than minus epsilon, which is minus epsilon times the Frobenius norm of A, because the Frobenius norm of A is 1, then it means that the minimum eigenvalue of 𝐺𝐴𝐺 transpose with good probability is going to be less than the trace of A minus this quantity epsilon times k. Now, k is the small dimension of this Gaussian matrix. We're going to figure out how we're going to set it later. I'm not going to give you the proof of this, but the rough idea here is, we're just going to look at 𝐺𝐴𝐺 transpose, and we're going to try to pick a vector W in the image of G transpose as close as possible to the actual negative eigenvector of A. Now, we can't get too close to it because G transpose and G have very small dimension. But still, you can get close enough to witness this gap, trace of A minus epsilon times k. Okay, so that's how you can prove this. On the other hand, you can show if A is actually PSD, then the minimum eigenvalue of 𝐺𝐴𝐺 transpose is at least the trace of A minus order root k, roughly. K is the small dimension. A is PSD. That is, all the eigenvalues concentrate around the trace of A. Again, I'm not going to prove this, but if you're interested in roughly how it works, the idea is, well, we're going to lower bound the quadratic form V transpose 𝐺𝐴𝐺 transpose V over a net of a k-dimensional subspace using the Hansen-Wright inequality. Okay, so basically it's just a net argument. Look at all possible vectors V and argue this quantity V transpose 𝐺𝐴𝐺 transpose V is at least this amount. And therefore the minimum eigenvalue is also at least this amount. I'll skip the details of that. But let me just summarize what we've shown, because now we can conclude with our final bound. We've shown that if our matrix is far from PSD, then the minimum eigenvalue of the sketch matrix is sufficiently away from the trace of the matrix A. On the other hand, if the input matrix is PSD, then the minimum eigenvalue of the sketch is close enough to the trace of A. Now, we'd like these two quantities to be separated so that our tester succeeds, and we can make them separated because all we have to do is set our small dimension k in our Gaussian matrix to be to satisfy that root k is larger than epsilon k. Okay, then it'll mean that this minimum eigenvalue in the PSD case is larger than the minimum eigenvalue in the non-PSD case. And just solving this inequality, we need our small dimension to be at least 1 over epsilon squared. Okay, and then we can distinguish these two cases. So let me just summarize what we've shown here. The algorithm is super simple. You compute 𝐺𝐴𝐺 transpose, where G is a Gaussian matrix, compute the minimum eigenvalue, and you set your small dimension of your Gaussian matrix appropriately to be 1 over epsilon squared, and you reject if this minimum eigenvalue is smaller than the trace of A minus a constant times root K. And you can figure out what this constant is from the analysis, and the trace of A you can estimate with additional sketching or dimensionality reduction techniques. So that's the whole algorithm. It requires 1 over epsilon to the 4th bilinear queries, or vector matrix vector queries, VMV queries, because you sketch on the left and the right with a Gaussian sketching matrix with 1 over epsilon squared dimensions. And this you can again show is optimal using a similar lower bound argument that we had before. Okay, so that's what I wanted to say about bilinear sketches. One cool thing I do want to mention, we're running short on time here, but what I wanted to say is that's actually a non-adaptive algorithm. You just sketch 𝐺𝐴𝐺 transpose, the end. Okay, super parallelizable. You can do it in a stream with updates to the entries of the matrix A, and so on. The natural question is, can adaptivity help for vector matrix vector queries, where you query on both the left and the right? Remember, when we began the talk, we looked at matrix vector queries, and adaptivity helped a lot. We formed this Krylov space where our next query was just the output of our previous query. So what about vector matrix vector algorithms? In fact, before our work, I wasn't aware of any algorithm that exploits adaptivity for vector matrix vector queries. So can we do better? Now, remember, for the L1 testing problem, we just sketched on the left and the right 𝐺𝐴𝐺 transpose, and we used 1 over epsilon squared queries. Can we beat this with adaptivity? And can we also beat it for P equals 2, where we had 1 over epsilon squared dimensions on both sides? And it turns out, yes, you can use adaptivity. You can get 1 over epsilon measurements instead of 1 over epsilon squared for P equals 1. And the idea, I don't have much time to say, but the idea is to try to minimize the quadratic form X transpose AX over vectors X using stochastic gradient descent. And it's kind of a novel way of using it. As far as I know, we're going to inject randomness artificially. Let me just tell you what the algorithm is. And you can think about the analysis or ask me offline. So what we're going to do is we're going to initialize our starting vector X to be a Gaussian vector. It's normal with mean 0. It's standard identity covariance. And we're going to try to do gradient descent. Okay, our next iterate, the k plus 1th iterate, xk plus 1, is our old iterate, xk, minus something really weird here. This is an unbiased estimate of the gradient. Okay, so the gradient of this function, x transpose ax, is just ax, or 1/2, or I mean 2ax. But it's ax up to a constant. And ax we can't actually compute in this model. It's a matrix vector query, and we only get vector matrix vector queries. So if you wanted to form every single entry of the vector ax, it would take a lot of queries. So instead, we're going to compute G transpose ax, axk in the kth iteration, where G is a Gaussian, but we still need to subtract a vector in this SGD algorithm. So we're going to subtract that number times this random direction G. Okay, and if you unfold what this quantity actually is, this is an unbiased estimator of the gradient. And so it's like, you can move this over here. It's actually G transpose dotted with the gradient. And so it's an unbiased estimator of the gradient. You can think of it as a stochastic gradient. Eta here is the step size. And we just keep iterating this procedure. And what we can show is the theorem is that if you actually have a large negative eigenvalue, then for a reasonably chosen step size eta, I won't say what it is, after about 1 over epsilon iterations, your quadratic form becomes negative. Okay, and of course, if your original matrix A is PhD, this quadratic form will never become negative. But your iterate will actually witness a negative quadratic form if it's not PhD. So it's kind of a cool use of dimensionality reduction inside of gradient descent, where you use a stochastic gradient formed by these vector matrix vector queries. I mentioned the result for p equals 1. You can apply it for L2 testers. You need a larger dimension of k is 1 over epsilon squared instead of k is 1 over epsilon. Roughly the idea is for L2 testing, remember we had this issue, well, hey, A might have a negative eigenvalue, but after sketching and getting 𝐺𝐴𝐺 transpose, all the eigenvalues are positive and concentrated around the trace. There's just this suspiciously small looking eigenvalue. Well, what we can do is we can do this shifting algorithm that we talked about earlier. We shift 𝐺𝐴𝐺 transpose by a multiple of the identity, which is roughly the trace of A minus this threshold we had where the negative eigenvalue is in the sketch, if it exists. By doing this shifting, we make this suspiciously small looking eigenvalue negative, and all the other ones are positive. And it turns out if you work out whatever the parameters are, it's not very important, but the shifted matrix has Shannon 1 norm, which is something, 1 over epsilon cubed. The negative eigenvalue, if it exists, has value 1 over epsilon. And so now you can just run this p equals 1 adaptive tester on this implicit matrix that you never have to explicitly compute. And at the end of the day, you get an adaptive L2 tester with 1 over epsilon squared queries instead of 1 over epsilon to the 4th, which is what you got by left and right multiplying by G, a Gaussian G. Okay, I'm almost out of time, and maybe PhD testing isn't your cup of tea, but let me just mention these techniques are quite powerful. So one thing we can do is actually estimate all the eigenvalues of an arbitrary matrix using these techniques. So if A is a symmetric D by D matrix, not necessarily PSD, then we can construct a sketch of A from which we can recover all the eigenvalues of A. We want to recover every eigenvalue up to some additive error, which I'm going to call epsilon times the Frobenius norm of A, which is the 2 norm of A. How small can such a sketch be? Well, there's some previous work, and I'm not going to get into it. It's work of Andoni and Nguyen. What it does is it takes your matrix A and it sketches on the left and the right by independent Gaussians, G and H. I don't have time to say the guarantees. I'm going to skip this, but let me just say that if you work it out, the size of G and H needs to be 1 over epsilon cubed on both sides. And moreover, their sketch destroys the sign information. It can't tell you if the eigenvalue is positive or negative. It can only estimate the absolute value of the eigenvalue. And what we show is instead, if you sketch on the left and the right-hand side by the same Gaussian matrix G, so 𝐺𝐴𝐺 transpose, then what you can do is, well, you have this problem that the expected value of 𝐺𝐴𝐺 transpose, all the eigenvalues are going to get shifted to be around the trace. This is the same problem we had for PSD testing. So instead, what we're going to do is we're going to subtract the multiple of the trace from 𝐺𝐴𝐺 transpose and then estimate the eigenvalues. Okay, since I think I'm out of time, let me just conclude with a slide which has the description of the algorithm. You can take this algorithm home. It's very simple. Here's how it works. You draw a random Gaussian matrix G. So the entries are normal with mean 0 and variance 1 over k. You compute the sketch S, which is 𝐺𝐴𝐺 transpose. Okay, super easy to compute. And then you just output the eigenvalues of your sketch minus a multiple of the identity. So you subtract the trace of A, and actually you subtract the trace of A over k, because these Gaussians had variance 1 over k. Whatever. You take your sketch, you subtract the multiple of the identity, and you just output the top k eigenvalues of your sketch. Those are estimates for your actual top k eigenvalues of A, and you output zeros for all the remaining eigenvalues. This is simple, easy to implement, and gives optimal guarantees. Namely, you can show that if your Gaussian matrix G has small dimension, 1 over epsilon squared, then you estimate all the eigenvalues of A up to additive error epsilon times the Frobenius norm of A. Okay, so any significant eigenvalue is estimated well from the sketch. So this, estimating the entire eigenspectrum, I think is a nice byproduct of the techniques that we developed for positive semi-definite testing. And let me just conclude in the interest of time. So we gave tight bounds for this positive semi-definite testing problem, which was useful for, say, second order optimization. If you have a Hessian, if it's PSD, maybe you've minimized your function. If it's not PSD and has a negative eigenvalue, then it's a good descent direction. So we gave algorithms with matrix vector products and vector matrix vector products for testing. If you're PSD or far from PSD, this model of matrix vector products and vector matrix vector products is very useful when your matrix A is not given to you explicitly, such as a huge matrix in optimization, the Hessian of a network. We used our techniques to develop sketches for eigenvalue approximation. We can approximate all the eigenvalues of a matrix. There are many open questions here. So our current sketching, what it does is it is a Gaussian sketch. It multiplies on the left and the right by a Gaussian matrix. And although the dimension is very small, the sketching matrix G itself is dense. And we don't know if we can use sparse sketching matrices. This is an important open question because if your matrix A itself is sparse, you might want algorithms that depend on the sparsity of your input matrix. Very fast algorithms. Other things that we don't really know if our spectrum estimation bounds are tight for adaptive measurements. Okay, so we have a non-adaptive sketching algorithm. And you could also consider other models for PSD testing, more general. Instead of having one large negative eigenvalue that you're trying to detect, maybe you have a lot of small negative eigenvalues. Can you try to find those? And so let me just conclude there. Thanks a lot for your attention. And I'm happy to answer any questions.
And at the beginning of the talk, you mentioned A is a Hessian matrix, but I don't follow how if that requirement entered the test for the PSD. Does that test hold for other matrices or generalized matrices?
Oh, yeah, thanks for the question. Yeah, the Hessian example, it was just an example. So this holds for any matrix A. You give me any matrix A, and as long as I can, you don't even have to give it to me in my hand. As long as I have the ability to perform matrix vector products with A, then I can execute my algorithm. So if I have A in my memory, then of course I can just multiply by a vector and get the output. But the reason I gave the Hessian example is because even if I don't have A in my memory, I can still multiply by a vector implicitly and get the output. That's useful because it's way too expensive to actually write down the Hessian of a large neural network. So yeah, just to clarify, this works for any matrix A, and that was just a motivating example for this model. I think I see a question to share the slides, and I'm happy to share the slides with the organizers. Yeah. Okay. Thank you, everyone. Bye bye.